عليكم السلام.
عليكم السلام.
وعليكم السلام.
Okay, today inshallah we will continue same subject, mathematical proof. I think we still have just a few slides from last lecture. Let me check first. Okay, yes. Okay. So today inshallah we will complete the mathematical proof and we will take another way for mathematical proof, which is mathematical induction. Okay, so this one was our lecture last week. Okay, which is logical inference and mathematical proof. So we took the inference rules like MP, MT, HS, DS, addition, simplification, conjunction, resolution, and we took some examples. Okay, in these examples, we have premises and conclusion. We start from the premises to reach the conclusion to prove that this argument that contain premises and conclusion, it's a valid argument. To prove that it's a valid argument, we start from the premises to reach the conclusion using the logical inference rule and also the logical equivalence rule. Then we take the mathematical proof, and we said that comparing with logical inference, it's informal. It's still formal, but it's more flexible. This is the meaning here, more flexible than logical inference rule. And we said that we have 4 types here for mathematical proof. First proof, which is direct proof. So we start from the assumption to get the conclusion. We start from P and reach Q. This is a direct proof. Then proof by contraposition. We have P implies Q. We start this time from not Q and we get not P. In this case, we said that P implies Q, also correct, because when we said not Q implies not P, it's equivalent to this one. So we start from not Q, we get not P, then We proved it. Prove by contradiction. Here we start from not P. If we reach something impossible, conflict, or something impossible, in this case means not P not correct, so P implies Q will be correct. So here in the contradiction, we will start from not P, yes, and reach something that impossible or have conflict. In this case, we prove that not P cannot happen. Then P implies Q, it's a correct one. Then P, it's correct. Proof by case, we did not take examples yet, but this when we have specific cases and we can apply it to the problem. So we apply the cases for the problem and we solve it. We will take examples. So let's continue with proof by contradiction. I think we stopped here, proof by contradiction. Okay, so I will start it from the beginning, proof by contradiction. Okay, so proof by contradiction, when we have to prove that P is correct, we will start from not P, and then we will reach something like R and not R. R and not R means something and it's positive. So this one, impossible, yes? Not really R and not R, any impossible result that we will get from not P, this mean not P, it's not correct. This mean P is correct. So in this example, said it proves that there is no, yes, no positive integer n such that n to power 3 plus 1 equal 100. So all this is P. We will start from not P. So we assume that not P is correct. Then if we reach contradiction, something not correct or impossible or contradiction with our assumption, then our assumption not correct. In this case, the original one, it's correct. So P here, there is no positive integer. So not P, we will say that there is a positive integer n. This is our assumption, which is not P. There is a positive integer n such that n to power 3 plus 1 equal 100. Now we want to prove this. If we did not prove this, then this one not correct, then P is correct at the beginning. If we prove that not P impossible to happen. Okay. How to prove this? To prove this, we need all the values of n. All values of n must be applied here. So, which values? We cannot say take the values 1, 2, 3, 4, all the values. It's not impossible, but we can take it as intervals. From the number line, we can take it as interval. For example, any number less than 2 and any number more than 3. This means all the integer value because we don't have a fraction, yes? But if we apply this, we will get value less than 100. We need to prove that. We need to prove that. This 100, we need to prove that any number we will take it will be less than 100 or more than 100. Any number. So we need two numbers to apply them here to prove that any number will be less than or more than 100. In this case, it's not equal 100. In this case, this one not correct, then the original one correct. This is our plan. So let's apply our plan. Which number could help us? We will take two numbers sequence, 2 and 3, 3 and 4, 4 and 5, to take the correct interval. If you try, for example, 2 and 3, if you apply 2 here, you will get 2 to power 3 plus 1. It's equal how much? It's equal 9. And the 3 to power 3, it's 27 plus 1, so 28. We did not reach this plan that we need it. So we will take more numbers because we need number less than 100, number more than 100. Give us result like this to prove that it's impossible to get 100. Okay. So we try to take now 4 and 5 to prove that any number less than 4 or more than 5, this means all the numbers will not give us 100, then not B is not correct, then B is correct. When we calculate it for 4 here, we get 4 to power 3 plus 1, it's 65. 65, it's less than 100. Okay, so there is no number less than 4 will be 100 because 4 it's give us 65. So any number less than 4 will give us also number less than 100. Okay, now take 5. Now we will take n more than or equal 5. 5 will give us 106, 5 to power 3, 125 plus 1, 160, 26. It's more than 100. So any number more than or equal 5 will give us number more than 100. So numbers less than 4 give us number less than 100. Number from 5 and more give us more than 100. So there is impossible to get number give us this one correct. In this case, not B is not correct. There is contradiction here with our assumption. This is a contradiction. We assume that not B is correct, but the result is contradict with our assumption. So our assumption not correct, not B not correct, then B is correct. This is a contradiction. We start from not B. This is a different because some students confuse between contradiction and contraposition. Contraposition, let's remind you by contraposition. Contraposition, the previous one, we start from the conclusion, not Q, not the conclusion, to get not B, to prove not B. And because this one equivalent to the original question or the original assumption, then the original assumption is correct. But contraposition, it's different way. We start from not B, not the assumption or the opposite of the given premises to get something that contradict with our assumption or something that impossible to happen. In this case, we prove that the opposite impossible, then the original statement is valid. Another example, also for contradiction. It proves that if 3n plus 2 is odd, then n is odd. Okay, so what's the given for us? This p, yes? The given for us 3n plus 2 is odd. So what's the opposite of odd? We will assume that n, this is the whole statement, yes? We will take its opposite. So n is odd, it's given to us. So we'll start from n is even. Okay, this question merges two ways, the contradiction with the contraposition, because we already have P implies Q here. Sometimes we have P only, like this question. Okay, so I think this proof it's very close to contraposition. So we assume that n is not odd, so it's even. If n is even, there's an integer k. This is the even equivalence. We take it last time. So 3n plus 2, we can write it as 3 multiplied by 2k. Why 2k? Because we take n as even, so n equal 2k. Okay, so it's equal 6k plus 2, so it's equal 2 multiply, we take 2 as common factor here, so divided by 2 we have 3k, divided by 2 we have plus 1. This k integer, so this one integer, 2 multiplied by any integer, it's give us what? Even. But we know that this one, it's odd. So this contradiction with the original assumption. So our assumption that this one even, it's this one odd. Sorry, this one even, it's not correct. So the original assumption, which is n must be odd, is correct. By the way, same question could be applied by contradiction, by direct, proof by contraposition. Sometimes if we said you are free, you can choose any way. But if we mention that you have to use direct proof, you have to use contraposition, you have to use X way, Y way, then you have to follow this way. We still have two ways, proof by cases, and the slide that we must start actually, this one is this lecture, which is proof by induction or inductive proof. Okay, so proof by cases, it's very simple one. Proof by cases, we will apply the cases. When we have specific cases, we can apply these cases to our problem to reach Q from the assumption. So if we have some assumption like this, P1 or P2, or it's logically equivalent to each one give us the conclusion and the other one and the other one. So the meaning here, we have cases, we will prove each cases, case P1, case P2, case P until case Pn. Everyone will give us the conclusion. In this case, we said that our assumption or argument is valid. This simple example. So this example says it proves that n plus 100 more than 3 to power n if n is a positive integer with n more than or equal 1 and n less than or equal 3. So how many cases we have? It's very simple. We said integer, so we don't have fraction. So we have case that when n equal 1, we have case when n equal 3, and we have case when n equal 2, because n between 1 and 3, including 1 and 3. So we have three cases. We have case when n equal 1, we have case when n equal 2, we have case when n equal 3. Okay, apply these cases here. When n equal 1, so we have 100 plus 1, 100 plus 1, and this is 3 to power 1, which is 3. So 100 plus 1, it's more than 3. Okay, so we proved first case. Second case, same issue. We will start with n plus 100, and now it's 2, so it's 102. Now we started from this one, 3 to power n, n2, so 3 to power 2, it's 9, and this correct, 102 more than 9, so it's, and 9 equal 3 to power 2, so it's correct. Same issue when we have the case 3. So this is 3 plus 100, it's 103, 3 to power 3, it's 27. So this condition is correct also for n equal 3. So we proved this by case. Here, as you can see, we have specific cases, but in some example, we have like a range, but we still have specific cases. Look here, it proves that if n is an integer, then n to power 2 more than or equal n. Okay, what cases we have? We take the cases if we have numbers from the number line like this. So we have integer when we have 0, because we have power here, yes. So this case 0 to power 2 and so on. So we will take this case when we have n0. So, and we will take this interval and this interval. This interval, we speak about integer, yes? So we already take 0. In this case, we will take that when n more than or equal 1 and n less than or equal minus 1. And we have to prove this. So we take the cases of n. We have three cases: when n equals 0, when n more than or equal 1, when n less than or equal minus 1. So when we have n equals 0, apply it here. This one become 0, and this one 0. 0 more than or equal 0? Yes. So we proved first case. Second case. Second case, when we have n more than or equal 1. Okay, apply it here. So when we have n more than or equal 1, this means n more than 0. So we can multiply n more than or equal 1. Yes. So n more than 0. Yes, because it's more than or equal 1. So it's more than 0, not including 0. Yes, it's more than 0. This is correct. Now multiply each side by n. Okay, this one n to power 2 more than still 0. Yes. So, and this one more than or equal this one more than or equal n. So when we take this and multiply each side, this means n more than or equal 1 more than 0. Multiply this one by n and multiply this one by n. You will change it, you will not change it. So this n to power 2 more than or equal this n. So this correct. Now the opposite. When n less than or equal minus 1. We said that n to power 2 from here, this more than 0, okay, n to power 2 more than or equal 0. Why more than or equal 0? Because any number to power 2, if it's not 0, it's more than or equal 0, even if it's equal 0. Okay. You know, power 2 of any number, it's more than or equal 0. So, n to power 2 more than or equal 0. And this more than minus 1. And we said that n less than or equal minus 1. So, minus 1 more than or equal n. In this case, n to power 2 more than or equal n. So we proved it. Again, I think some of you lose in the middle. I will return it for you. So, proof by case. How many cases we will have here? 0 and anything more, anything less. So, we have here less than sorry, this positive. More than or equal 1, and any number minus means any number less than or equal minus 1. Okay. First case, 0, it's direct. Yes, here it's 0. Okay, and here 0, so it's less than or equal. Second case, we start from this one to get this one. To get this one, look here. We have n more than or equal 1. Multiply this one by n and this side by n. This will not change. When you have an equation, mathematical equation, and you multiply both sides by the same number, you will not change the equation, yes? So we will multiply both sides by n. So this one, n to power 2 more than or equal n. We get also this one. So it's correct. Okay. Now, third case. Third case, you have to focus. It's easy also, but you have to focus a little bit with it. Third case says like this. We take now the third case, n less than or equal minus 1. This is the third case. Look. Hence means we know that. We said in mathematical proof, we take the axiom, something that already known, we can use it. We said that n less than or equal minus 1. Any minus number, minus 1, minus 2, minus 3, minus 100, if you make it to power 2, you will get number more than or equal 0. Yes or not? Yes, because minus to power 2, it's positive, become positive. So this one equal 1, which is more than or equal 0. This one give you 4, which is more than or equal 0. This one give you 9, which is more than. So any number here, any negative number to power 2 will be more than or equal 0. So this first part. And of course, 0 more than minus 1. And in our case here, n less than or equal minus 1. Okay, then n to power 2, this side, more than or equal n. So we get the conclusion correctly in this case, in case 3, in case 2, and in case 1. And that's what we need to improve. Okay, you can try these exercises at home. Exercise 1 to 18 from the book, page 91. This one must be from the previous lecture, actually. Today we have another subject related to mathematical proof also, which is mathematical induction. As you can see here, the style little bit different because this slide from the book, so it's not prepared from me. That's why I cannot write my name on it. Yes, it's not mine, this one. But let me just at least mention the week. Okay. So this week 4. And this subject actually from the book Rosen, this is the name of the book, section 5.1 in the book, mathematical induction. Okay, if you study programming, there is something called recursive function in programming. You remember the recursive function. It's actually recursive function. It's use the idea of mathematical induction. Mathematical induction, it's like the recursive. Okay, just okay. So, what is the induction actually? It's type of mathematical proof. Okay, um, we use it only for proof. Okay, it's have three parts. Three parts. First part, we have the base case. We get one of the cases and prove that it's true. For example, if we have equation, n equations that have number n, for example, n factorial, okay, equal something. To prove it, we take first case that n equal 1. We call this base case, okay? So the simplest case, we take it and prove that it's true, it's correct. Second part, we make hypothesis, we make assumption from ourselves. We said that we assume that this statement, it's true for a given element, for element K, for example. We don't know which element. Let's say element K. So we assume assumptions is mean from ourselves. We said that we will consider that it's true. It's not yet true. We will prove that it's true. But at the beginning, we will assume that it's true. So for n equal k, we said that we assume that it's true. So we take, in this case, k factorial as true for this question as example. Okay. So we take the base case, then we assume that it's true for case k. We don't know what this case. And then starting from this assumption, okay, we will show that the next element of our assumption, next element means when n equal k plus 1. Now we have to show that for this next element, it's true. When we show that for the next element, it's true, then for our assumption is it true, then all the statements or all the equation will be true. So this, the induction. It's very similar to a recursive function, yes? So we will take examples. So it's like this. We start from first one, then we will say that specific one is true, then next one is true. Then we prove that next one is true depending on this one. What this will give us? If k plus 1 is true, depending on that k is true, then if we take k as 1, we already said that k is true, and we get k plus 1 is true. So next time when we take k as 2, we already know that for 2 it's correct, then for 2 plus 1 it will be correct. That's the meaning of the induction. Let's take example. This example asks you to show means proof, that the sum, okay, you know the summation, shows that the summation of the first n odd integer, this means from I equal 1, because we speak about first n odd integers until n, okay, summation of I from I equal 1 to n, is n to power 2. So this one equal n to power 2, given that n is odd. You know when n is odd? When we have 2i plus 1 or minus 1. What's the general form for the odd? 2k plus 1, yes? This is the general form for the odd. But this, if we take the number from 0 to n. But here we take the number from 1. When we start from 1, we will take this one as 2k minus 1. This also general form for the odd. General form for the odd from 1. Because we speak about first n odd integer. This means start from 1 to n. In this case, we will take n as 2k or I in our example, minus 1, because we start from 1. When n equal 1, so 2 multiplied by 1, it's 2 minus 1, it's equal 1. So you get first odd number. When n equal 2, 2 multiplied by 2, it's 4 minus 1. So you get 3. That's why we take the general form minus 1, because we started from 1. When we started from 0, we can take it plus 1, because 0 multiplied by 2 is 0 plus 1. It gives us 1. Okay. So this only thinking about the question. So the question, it says like this. It says, this give you only example, what's the meaning of the question. The meaning of the question, if we have n equal 5, first 5, for example, only, odd integer is n to power 2. This is the summation of. Let's try. When n equal 5, first n summation, n odd integer. N means 5 odd integer. Let's count 5 odd integer. Okay, we have 1, this first odd integer. The next odd integer, it's a 3. Next one, it's 5. Next one is 7. Next one is 9. How many one? 1, 2, 3, 4, 5. So this first 5 odd integer. Okay, now this first 5 odd integer, we need the summation of them. The summation of them have to give us n to power 2, which is how much n to power 2? n5 to power 2 means 25. So get the summation. 1 plus 3 plus 5 plus 7 plus 9, you will get 25, which is 5 to power 2. This only example to show you that this one correct, but you will not use examples. We need to use what? Mathematical induction, a proof. So how to prove? First, to make the proof, we have to write this as equation. To write this as equation, for all n, we have the equation Pn, it's the name of the equation, where Pn, it's given to you here, equals the summation from 1 to n, from I equal 1 to n, and this is the summation. This is the general form for odd, which is we have 2 multiplied by I minus 1. It must give us, look here, we have 2 equal. What's the meaning of 2 equal? We need to prove this, that it's equal to n to power 2. So this is the writing of the equation, the writing of this statement as equation. The equation is, or the mathematical expression here, P n, it's equal to summation from 1 to n, first n odd from 1 to n, because it's odd, it's summation for 2i minus 1. This is the general form of the odd. If they said even, then 2i. We take the general form for the even. Okay. We have to prove that this one equal n to power 2. To prove this, using mathematical induction, first of all, we will take the base case. What's the base case? When we have n equal 1. So we take first the base case. We will show that P1 means when we have n equal 1, we have to show that it's true. How to show it's true? We take n as 1. When you take n as 1, so I from 1 to 1. So I equal 1. So this when we have the case n equal 1, it's the base case. So it's equal to summation for I from 1 to 1. So we will apply I here. We will take 2 multiplied by 1 minus 1. 2 multiplied by 1, it's 2. Minus 1, it's 1. So this is the left side. Right side, 1 to power 2, or 1 square, it's 1. So left side 1, right side 1. So base case is true. Now we take the next case, which is the assumption. We assume that, okay, so we continue with the example. This first step, base case. Second step, we called it induction. This is a process. Inductive, this is the name of the hypothesis. It's come from induction, yes? So inductive hypothesis. The inductive hypothesis, something that we will assume. We will assume that the equation is correct for K. So it's assumption. It's not given for us. We assume that it's correct. Let's write it for K. When we write it for K, we will have the equation P for K. Instead of N, now we will write K. So instead of N, we write K. The equation is from I equal 1, summation from I equal 1 to K, for 2I minus K, we need to, or it must be equivalent to K to power 2. From where we get this? From the given for us here. This is the original equation. Yes. Instead of N, we will put K. So this K, and this one K. We assume that it's correct for K. Okay. So this is the inductive hypothesis. Third part, we will prove that for k plus 1, it's correct. We will use k plus 1 in this side, and we reach k plus 1 for the other side. So now third step, which is called the inductive step. So base case, then second step, inductive hypothesis. We assume that it's correct for k. Third, we have to prove the inductive step. What's the inductive step? We have to prove, to show that this one true for k plus 1. So remember, what the equation was? The equation was summation for I equal 1, the original one, okay, from the previous page. It's summation for I equal 1 until n for 2i minus 1. It's must be equivalent to n to power 2. This is the original equation, yes? Now, in this original equation, we will take n equal k plus 1. So this is the inductive step. We have to show that it's true for k plus 1. Okay, so for k plus 1, inside here, it's actually I from equal 1 until, instead of n, now we will put that k plus 1. So n become k plus 1, 2i minus 1, and n to power 2, it's k plus 1 to power 2. Now we have to show that this one is true. How to show that this one is true? We will use our assumption. If we get it true, then our assumption is true, then the whole statement or the whole equation true. Okay, let's do it. Next step, from we need to show that this one is true. Okay, this is the next step. We need to show that this one is true, and we have this one true as assumption from us. We will use this one here. So this is our hypothesis. Just I copied it here. This same. This one, we copy it because we need it. So we need to remember it. Okay. This is our assumption, our hypothesis. Now, we need to prove the inductive step. First of all, this is the inductive step. Look to it. Summation from 1 to k plus 1. So we take k plus 1 here. Okay. So when we take k plus 1, we applied it inside, yes? So apply k plus 1 here. It's 2. Instead of I now, we will take k plus 1. This one, we can write it as, just remember, it's summation from 1 to k plus 1. So it's summation from 1 to k plus, doesn't matter what inside, just show you that we can plus k plus 1 for this equation, yes? So it's like this. We divide it to summation from 1 to k plus the equation with k plus 1. So take the equation for k plus 1. This is only to show you what we mean. It's not part from the answer. Okay. So take it for k plus 1. K plus 1 here. The value of I, we will take it as k plus 1. So 2 k plus 1 instead of I minus 1. All this plus what still we have in the summation. We have in the summation from 1 to k because we already take k plus 1 here outside. So what still we have? Summation from I equal 1 to k to I minus 1. Okay, so this so we write this equation this way. Just we take it as two parts for k plus 1 and summation from 1 to k because next term it's k plus 1. If you take k, then from 1 to k minus 1. If you take another summation and so on. So we take k plus 1. Look to this one. What's this one? It's same like our assumption. So we have left side. We can write instead of it the right side. So instead of this part, we will write k to power 2 from our assumption. We said that next step is the assumption for k. So we have already in our question here the left side. So we can take the right side. So instead of this one, we can write k to power 2. And we still have here 2 multiplied by k plus 1 minus 2. We will make the 2 inside. So it's 2k plus 2 minus 1 plus k to power 2. So let's reorder it. It's k to power 2 plus 2k. 2 minus 1 it's 1. So plus 1. So this what? This is the left hand side. Take the right hand side. The right hand side, k to power k plus 2 to power 2. It's a perfect square. You know this equation? Perfect square. X plus 1 to power 2. You can calculate it. It's perfect square. It's the square of x plus the two term x multiplied by 1 multiplied by 2. So plus 2x plus 1 square is 1. So this is a perfect square equation. You must know it from the school, from anywhere. It's basic uh, mathematics. Okay. How many one knows a perfect square? Raise your hand. I want to know your levels. Wow. Only few. Friends, basic mathematics, it's not our job to return for the basic mathematics. You have to know how to solve equation from the school. We will not return for every time for the basic equation. It's basic, yes? So this perfect square, it's a basic equation. I think red color, it's not good with this background, I think. Let me try to change the red color. Which color will be more perfect on this background? I don't know why this background. Let me see this one. I'm trying just to change the color to one. Just help me to select a more comfortable color for your eyes. Which color could be better now? Because the background have blue, so I feel that it's maybe the black color could be.
Sir, I guess the black color must be the
Okay, I
best
think the
one.
black color will be better here. Or
I think the best choice is black color.
yes, because I see that the red color little bit have conflict with the background. Yes, so I will use the black color.
It's a little bit.
Yes, so we already reached the left-hand side. We reached this one. So now take the right-hand side. Right-hand side, it's a perfect square for k plus 1. So it's k to power 2 plus k multiplied by 1 multiplied by 2, which is 2k plus 1 square, which is 1. Look to right-hand side and left-hand side. You will see that they are same. So, using the hypothesis that we make assumption in the second step, this one, we proved the inductive step. In this case, we have the base case correct. We assume the hypothesis, and from the hypothesis, we prove the next step, which is the inductive step. It's true. So the original statement is true. From where we get that the original statement is true? We make the hypothesis ourselves. How come it's true? I will show you why it's true. Look to this the steps, okay? I make it with you, okay? This k plus 1, we take it outside. We still have k from 1 to k. Then this one, we take the equivalent from our assumption. We take it here. Then we get this one, k to power 2 plus 2k, which is same as perfect square. So they are equivalent, so this is correct. From where this induction come? This is the question. Okay, what we need to show from this induction? Okay, first of all, we said that it's for p plus 1 is correct. We get it. This we proved it here. Let me just clear the screen. We proved it. By the way, mathematical induction take less space than this. Just we show you the details here. So we get it is true for P1, yes? Then second step, we assume ourselves that it's correct here. Then we proved using this that for k plus 1, it's true. So how come it's true? Like this. We show it for p plus 1. Yes, this is the base case. Then for pk, we assume that it's true. Then we assume that it's true. So if it's for pk, it's true. We show that in this case, for pk plus 1, p means the polynomial or the equation, mathematical equation, our mathematical equation. It's true. When it's true for k, we show that it's true for k plus 1. Yes? Okay. So, we know it's true for p plus 1. So, when we take k as p, we know it's true for p plus 1. And we show that if it's true for p1, it's true for p2. Yes or not? We show it. We show this one. That if it's true for k, it's true for k plus 1. So, we prove this one, and we have the original case. Okay, but why the whole statement is correct? The whole statement is correct. Let's follow the steps. If it's true for P1, it must be true for P2 because we said this, we prove this here. Yes? But this was our assumption. But here we proved it. We get it for the base case. So this for sure true. And in this case, it's for sure here true. Now take the next step. For P2, it's true. We get it from here. So it's true for B3 because when we take k equal 2, when k equal plus 1, so it's when we have 3, it's true. And also because B3 is true, for B4 is true. And because for P4, so because for PK is true, for PK plus 1 is true. Instead of one by one we take this one general as K and this general as K plus 1. So this what we are showing using the mathematical induction. Okay, that's from where this mathematical induction comes. So again, shortly, mathematical induction have 3 steps. First, shows a base case. Second, shows the inductive hypothesis or assume instead of show, assume the inductive hypothesis. This means for k term. This almost for one term except for first term, except if the first term it's not 1 in some cases. Okay. Then manipulate means get the inductive step. Okay. This third one. So fourth step, we use this inductive step, or we show that this inductive step. So this two actually it's same step. You can consider it as third step. This 2 point. We write the inductive step and we prove it. We prove the inductive step using what? Using the hypothesis. Okay. Another example. It's actually a simple subject. Okay, we can take a break 10 minutes until 11 and we continue. Inshallah, this subject we will finish it today, inshallah. Okay, so 10 minutes break. Assalamu alaikum again. So, are you ready? How many want ready around us? Raise your hand, please.
I'm ready.
Yes, Ahmed, you always ready. Okay, so let's continue. Second example. So, shortly, we have 3 steps. Phase, then hypothesis for K term, then inductive step for K plus 1. This we show it, the base, this we assume it's true, and this we show it using our assumption. Okay, so this is a question also from the book section 5.1. Show the summation of the first n positive even integers is n to power 2 plus n. So you can write it, yes, summation okay, from I equal 1 to n. Okay, positive even integer. Even integer, the general form is 2i. Yes, so summation of 2i. We need to show it that it's equal n to power 2 plus n. So we write our equation. Of course, for all of n, okay, we have Pn equals this one. Okay. So this is our equation as I wrote it for you. So for all n, we have polynomial n where Pn equal from n equal 1, from I equal 1 to n, summation for 2i. From where we get this 2i, it's the general form for the even integer. Okay. We need to show that this one equal n to power 2 plus 2, plus n, sorry. Okay, first step, which is base case. Second step, which is inductive hypothesis for K. Base case, okay, always it's first one. So we will say it, see it for 1. Inductive step, we have to show it for K plus 1. Okay. So for P1 means when n equal 1. So it's summation from I equal 1 to 1. So this equal, instead of n, we put 1. So this one equal 2. 1 to power, or 1 square, it's 1, plus 1, it's 2. This is the right-hand side. The left-hand side, it's 2 multiplied by I, which is 1. So it's 2 multiplied by 1, so it's 2. So left-hand side 2, right-hand side 2. So it's correct, the base case. Now, inductive hypothesis, we assume, doesn't matter, here's the pronunciation. We assume that it's correct for Pk. So instead of n, we take k. So we assume that it's correct from I equal 1, the summation from I equal 1 to k for 2I equal k to power 2 plus k. So this is our assumption. Now we have to show that the inductive or the inductive step is correct. What's the inductive step? The next step, which is for k plus 1. So we need to show that this is correct for k plus 1. So we will take n equal k plus 1. Instead of n, we put k plus 1, we put k plus 1, k plus 1, k plus 1. Now, forget the right-hand side. We will return for it. Let's start with the left-hand side. Always take the term k plus 1 outside to get term k plus 1 plus term k. Then you can take k from our assumption. Yes? So it's like this. We write this, just we remember the second step, which is the inductive hypothesis for k. Okay. Then this for k plus 1. How to calculate it? We take k plus 1 outside. Okay, so instead of I, we take I as k plus 1. So 2, instead of I, now we will put k plus 1. So this one, we will divide it into two things. When k plus 1 plus the summation for I equal 1 to k. Yes? Same idea always. Okay. So we write this one as, instead of I, now we will take the term k plus 1, 2 multiplied by k plus 1. All this plus the summation. What is still in the summation? We take one term, k plus 1. We still have from I equal 1 to k to I. Now, look to this one. It's here. So we have the left side. We can take the right side instead of it. So this one equal 2. This one down. 2k plus 2. How come? 2 multiplied by k, 2 multiplied by 1. Okay, a plus. Now this one, we will take k to power 2 plus k. So plus k to power 2 plus k. Just organize this again. So it's k to power 2, k with 2k, then it's a plus 3k plus 2. Okay, this one what? This one, the left hand side here. So this left hand side, we take it here. Now let's see the right hand side. Right hand side, k plus 1 to power 2, we just mentioned it. It's a perfect square, this part. Okay, let's just try again. This part, we just mentioned it. It's a perfect square. What its equivalent? k to power 2 plus k multiplied by 1 multiplied by 2 means plus 2k plus 1 square, which is 1. Okay, now this one plus k plus 1. K plus 1 plus k plus 1. Okay, organize it. K to power 2. 2k plus k, it's plus 3k. 1 plus 1, it's plus 2. Look to the right-hand side and left-hand side. They are same. They are same, so we proved the inductive step. So we have the base case, we have the assumption for the inductive hypothesis. Then we prove the inductive step using this hypothesis. Then we proved the original statement. Okay, this only the steps that I showed to you. Okay. I already mentioned all this. Let's just describe to you how we get the steps. I already show you the steps. Okay, third example. Let me just check how many examples we still have. Third example. Then, okay. Then fourth example. Okay. We still have around 3 examples. Okay, third example. Third example says, it's direct one. You have this equation. It's already given to you. You need to prove it. So we have left-hand side, right-hand side. We need to prove it. Again, 3 steps. First step, base case, when n equal 1. Take n equal 1, so it's summation from I equal 1 to 1 for I to power 2. So I power 2 or square, so it's 1. Now take the right-hand side. We put n as 1. Okay, so it's 1 multiplied by 1 plus 1 multiplied by 2 multiplied by 1 plus 1. So 2 multiplied by 1, which is 2 plus 1. Okay, all divided by 6. This is the question given to you. This is the base case. So 1 plus 1 is 2 multiplied by 1, so it's 2 multiplied by 2 plus 1, which is 3. So it's 6 divided by 6, which is 1. So left-hand side 1, right-hand side 1. In this case, the base case is correct. Okay, now inductive hypothesis. We assume that it's correct for K. So we assume that it's correct when we have n equal K. Apply K here instead of n. So we have left-hand side from I equal 1 to K for I square. It's equal to K multiplied by K plus 1 multiplied by 2K instead of NK now, plus 1, all divided by 6. So this assumption, we assume that it's true. We assume, we did not yet prove that. But we will use this assumption to prove the third step, which is inductive step. We show that it's true for k plus 1. What's the meaning for k plus 1? For n equal k plus 1. So this means we have to show that from I equal 1, summation from I equal 1 to k plus 1 for I square, it's equivalent to, instead of n, k plus 1. Remember the original left-hand side, it's like this, n multiplied by n plus 1 multiplied by 2n plus 1 all divided by 6. This is the original statement here, as you can see. Okay, now instead of n, we will put k plus 1. So k plus 1 multiply by, here, k plus 1 plus 1. So k plus 1 plus 1 multiply by 2 instead of n, k plus 1. So 2k plus 1 plus 1 divided by 6. Okay, we can just organize this one, the right-hand side. So it's k plus 1 multiplied by k plus 2, k plus 1 plus 1, k plus 2 multiplied by 2k plus 2 plus 1. So 2k plus 2 plus 3, all divided by 6. So this is just we reorganize the right-hand side. Okay, now let's start with the left-hand side. As usual, we take k plus 1 outside. So in I, it's equal k plus 1. So it's k plus 1 this side. We divide it into two summation, k plus 1 to power 2 when I equal k plus summation okay, summation of what? From I equal 1 to k I square. Okay, this one we can take it as k plus 1 square. It's a perfect square, yes? So it's k square plus 2k plus 1. This side, we can take it from our assumption. Here, our assumption. Sorry, here. So we have this part, as you can see it here. We have this part from I equal 1 to k I square. You can see it here. So we can take this side. Okay, take this side, which is okay. Let me just before open this, let it as it k plus 1 square, and I will take this side plus which is k multiplied by k multiplied by what? Multiply, let me remember from here. Multiply by k plus 1 multiplied by 2k plus 1. Okay. Multiply by k plus 1 multiply by 2k plus 1. Okay, what's this? All this left hand side. We have to show that it's equal right hand side. Okay, to make it simple, okay, what will happen if I multiply right hand side and left hand side by 6? It will not change anything. If you have equations that have left hand side and right hand side, and you multiply left hand side and right hand side with the same number, this will not change anything, yes? Because when you multiply both sides with the same number, this don't change anything. So I will multiply the left hand side and right hand side by 6. Why? Just to eliminate this 6. I don't need in the division to have this 6. Make it much simple for me. So I will multiply this side by 6 and this side by 6. This will not change the equation. When you multiply both sides with the same number, you don't change the result. So multiplying right hand side by 6, we have what? We have k plus 1 multiplied by k plus 2 multiplied by 2k plus 3. Okay, this equal. Now multiply this side by 6. You will have 6k plus 1 to the power 2. We multiply this by 6. And this by 6, we remove this 6. So plus k multiplied by k plus 1 multiplied by 2k plus 1. Okay. Now, let's open this one. It's k to power 2 multiplied by 6. So 6k to power 2 plus k multiplied by 1. This is a perfect square. K plus 1 to power 2. It's k square multiplied by 6. So 6k square. Then k multiplied by 1, k multiplied by 2, 2k multiplied by 6, so 12k plus 1 square, because it's inside the perfect square, so it's 1 multiplied by 6, so plus 6 plus. Now let's calculate this one. It's k multiplied by k, so k square plus k. K inside. K by k, k square. K by 1, k. All this multiplied by what? 2k plus 1. We can also open this one. This one, k multiplied by k, k multiplied by 2, Okay, so this one must be equal. This left-hand side, right-hand side. K to power 2 plus 2k plus k plus 2. This all multiplied by 2k plus 3. Yes, it's long, yes. To make it short, we can take the final result. Just you need to calculate this one. You will multiply this one by this one here, this one here, this one here, and then make summation. You will have k to power 3 actually in this result. So let me take the calculation directly. So we have k plus 1 here. We have the remaining one. Instead of it, we remember this one from our assumption from the previous slide for assumption for k. So we will apply it here. Yes. So apply it here. The equation like this. Now multiply each side by 6. So we remove 6 from here, remove 6 from here, add 6 here. This when you multiply it. When you make the calculation, you will have this side like this. 2k to power 3, 9k to power 2, plus 13k. This is the left-hand side. And when you calculate this right-hand side, it will give you this result. If you look, left-hand side and right-hand side, same. So the inductive step, it's true from the inductive hypothesis, and the base case is true. So that's all. We prove our example. Okay. What if the hypothesis is not correct? Let's take this example. Show that, look, this same example here, same example, but we take this one plus 2. Is it correct? Let's see if it's correct. So, show that this equation is correct. To show that it's correct, first we will take the base case. Base case when we have n equal 1. So apply n equal 1 here. Summation from 1 to 1 for I. So it's 1 to power 2, so it's 1. Now apply n equal 1 here. So you have 1 multiplied by 1 plus 1. Then 2 multiplied by 1. So it's 2 plus 2 divided by 6. Calculate this one. 2 multiplied by 1. So it's 2. 2 plus 2, it's 4. So this multiplied by 4. Okay, something in the calculation here, I feel it's not correct. 1 plus 1, it's 2 multiplied by 1, so it's 2 multiplied by 2, so it's 8. Yes? By the way, it's not my slide. It's, it's a slide from the book author, not from me. So, again, to be sure that he wrote it not correctly, this one plus 1, because n equal 1. This 2 multiplied by 1, so 2 plus 2. So 2 multiplied by 1, it's 2 multiplied by 4, so this one 8, yes. The correct that this one must be 8. Anyway, 8 divided by 6, it's not equal 1 anyway. So base case not correct, no need for the next step. Finished. Then from the beginning, the equation not correct because the base case not correct. So if the base case not correct, the equation not correct. Sometimes you make assumption, okay, and from the assumption, you get that the inductive step not correct, like what we did. If you have a question like this, and base case will be enough. But for us to show you examples that sometimes the base case correct and we need to continue, and you will find that it's not correct in the inductive step. So let's see it. Let's continue as it's, we did not find it not correct. Let's continue anyway. Okay. Inductive hypothesis, when we have n equal k, you will write it like this. Okay, instead of n, we will write k. And instead of n here, we will write k. So it's from I equal 1 to k for I square equal k multiplied by k plus 1 multiplied by 2k plus 2. Now, inductive step. Inductive step, it's to show k plus 1. So we will write from I equal 1 to k plus 1. As usual, we take this one. We take the summation of k plus 1 outside. Then we still have summation of from I to k. And we take it from the original one. This one. We take it from our assumption. So this is our assumption. We take it. And at the end, you will reach something like this. This is the left-hand side, the right-hand side. And when you calculate the left-hand side and right-hand side, you will see that, okay, first term, like first term, second term, second term, third term, and third term, it's not same. Fourth term, fourth term, not same. So they are not equivalent. If the inductive step shows that left side not equal to the right side, then we assume that, or we found that this equation from the beginning, it's not correct. Okay. If you have this equation, you don't need to do the second and third step. From the base case, we show that the question not correct. But we continue to show you what? In some question, base case correct, but the inductive not correct. So if base case correct, you can continue at the end, you will find that the inductive, it's not correct in some questions. So you found that the original equation not correct. Fourth inductive example. Okay, is it last one? Oh, yes. Good that it's last one. I think we will finish early, inshallah. Hopefully. Okay, this simple equation. Fourth inductive example says that it's a question number 14 from the book, Frozen book. So show that n factorial less than n to power n for all n more than 1. Okay. Look here. You have to focus. We said for all n more than 1. What this mean? This mean n more than or equal 2. So base case here, not 1. Base case is 2, not 1. You have to focus in this. We did not say for n more than or equal 1. No. We said for n more than 1. More than 1 means the first term is 2, not 1. So this base case, so first case, base case is when n equal 2. Let's apply when n equal to n square, n factorial. We need to show that n factorial less than n to power n. N factorial means 2 factorial. 2 factorial, it's what? 2 multiplied by 1, so it's 2. Okay. And n, which is 2 to power 2, so this 2 factorial, it's equal to 2 to power 2, which is 4. So, yes, 2 less than 4. So it's correct for the base case. Focus here. Our base case is 2. Why not 1? Because n more than 1. More than 1 means more than or equal 2. So first term is 2, not 1. Okay, we show it for the base case. Now, inductive hypothesis, we assume that k factorial instead of n, now we will write k factorial less than k to power k. Now we don't have summation, yes? So now inductive step. Inductive step, it's to show that k plus 1 is correct. So instead of n, we put k plus 1. So k plus 1 factorial less than k plus 1 to power k plus 1. Let's now work on the left hand side. K plus 1 factorial. It's k plus 1 multiplied by k plus 1 minus 1 factorial. You remember that n factorial, this is the general term for n. N factorial, it's n multiplied by n minus 1 factorial. Yes? So when we said k plus 1 factorial, it's equal to, we take k plus 1 outside, k plus 1 multiplied by, instead of n, k plus 1. K plus 1 minus 1 all factorial. So it's equal k plus 1 multiplied by k plus 1 minus 1, which is k factorial. Yes? So we can write this one, k plus 1 factorial, as k plus 1 multiplied by k factorial. Okay. Instead of k factorial, we can take this one. But don't forget that it's not equal. It's less than. So k plus 1 factorial, it's equal to k plus 1 multiplied by k factorial. Okay, and this one less than. Why we write less than? Because instead of k factorial, we will take k to power k. But this not equal, it's less than. So this we take instead of this one k to power k, but it's become less than. Yes? Okay. So we take again, instead of k factorial, we take the right hand side, which is k to power k, but this less than. Okay. Now this one what? This is the left hand side. Let's take a look here. This one, actually, we can write it as k plus 1 to power 1 multiplied by k plus 1 to power k. Yes, because when we make multiplication, we make summation for the power. Yes, if we have same term like this, x to power 2 multiplied by x to power 4, for example, it's equal x power 2 plus 4. Yes, so same idea here. When you have summation or you have sum for the power, so you can divide it. Okay, so this one here. Okay, this one, it's more than this one. It's clear because we have k plus 1, and instead k to power k, we have k plus 1. Of course, k plus 1 to power k, of course, it's more than k to power k. Yes, k plus 1 to power k, of course, it's more than k to power k, because 5 to power 5, of course, it's less than 6 to power 5. Here, if k equal 5, and so on. So always k plus 1 to power k, it's greater than k plus 1. So shortly here, this left hand side, it's greater than right hand side, it's greater than left hand side. This right hand side, this left hand side. How come you know that it's greater? Because we have k plus 1 with k plus 1. But we still have k to power k and k plus 1 to power k. Of course, k plus 1 to power k, it's greater than k to power k. So it's correct. And if it's correct, this means our assumption is correct and the statement from the original is correct. Here we start from the right to get this one. Here we start from the left to get this one. Then we found that this one actually less than this one. And this gives us that left hand side is actually, yes, it's less than right hand side. Mathematical induction actually needs some thinking from you and need more practice, because more questions you solve, more ideas you will get. The book have many questions. you can try, this is my suggestion, but you can try more questions. Okay? And I will give you later more exercises. You can try at home exercises 13 to 15 and 20 to 25. I did not mention all the questions, but if you solve all the questions, it will be good also at page 330 of the book. That's all for today. If you have any question before we finish. Sorry, Abdullah. Which question? I did not read your question. Because I cannot see the slides and your question at the same time. So, your question for which example? Okay, you get it. Okay. Doctor, someone removing me. I don't know. I will see how to solve that problem. Okay, Fatih, of course, I already shared the book on our Telegram group. I wonder if you did not join our Telegram group yet. You are not with us, Fatih. I mentioned many times, and this means you did not open OAS system. You have to open OAS system also, and in OAS system, I shared the Telegram group. You have to be in our Telegram group. So let me share the code with you now. Open OAS system, you will find that Telegram group code. Anyway, I can write it here. Okay, discrete mathematic. And this is a link. No problem, this is a link. I will try to send it using OAS system because there is no excuse. Everyone must join this Telegram group. I did not share yet this one. We are at week 4, and this is our lecture note for week 4. I will share it today. I will share it now, today. Okay, that's all. Thank you for attending the lecture, and see you. I'm not sure yet, but it's of course a classic. I mean, I'm not sure if it's face-to-face or not, but for sure the exam will be classic. We don't do the exam, it's mathematic. How to do it as a test using Unica? It's not possible. Okay, take care, everyone. Thank you. See you.